So in the last video, we looked at this Ethernet signal and we decoded each of the bits by using this, these symbols over here. So a 0 is represented as a positive voltage transitioning to a negative voltage, and a 1 is a negative voltage transitioning to a positive voltage. And so we decoded each of these bits, and then we kind of flipped the order of the bits for each of the bytes. And this byte is, when we convert to decimal, is 75, which is a K. And then this byte is a 65, which is an A, and so we're sending KA. But you might be wondering how we knew, or more importantly, how a receiving computer would know that that these particular group of 8 bits make up the bytes. You know, presumably there's a whole stream of like ones and zeros off here to the left, and that stream is going to continue off to the right as well. So what happens if we pick, the wrong group of 8 bits? So here, for example, we're starting with like the third of these bits that's shown here. But what happens if we start instead with the fourth? So maybe we draw our boundaries here. Aren't we going to end up with something else? So here we have the 2 more groups of 8 bits, and we've reversed the order there. But now if we convert these 8 bits to decimal, this is equal to 165, and that actually maps to, if we map it to a symbol, depending on what character set we're using, this is the yen symbol. And this one over here, if we convert this to decimal, is 160. And that maps to just a blank space. So if we meant to send the letters KA, and the receiver is interpreting this as yen space, then clearly something has gone very wrong. So how does the receiver know what the correct byte boundaries are? So how does it know that this byte should start here, or actually start over here and not here or here or here or anywhere else? Well, so the way it knows is that bytes are grouped into something called frames, which might be 1,000 or so bytes long. And if we have a way of telling where a frame begins, then we can use that to find the byte boundaries. So hopefully if I show you a couple examples, this will make a bit more sense. So I'm going to show you 2 different ways of doing framing that are used in networks. There are many others, but this should give you a sense. The first framing mechanism that I want to talk about is used by a protocol called HDLC, which stands for High-Level Data Link Control. And this is a protocol that's used pretty commonly in internet service provider networks and other large networks. And so what HDLC does is it uses a special bit pattern called a frame delimiter, or a flag. And this pattern with HDLC is just defined to be 0, 1, 1, 1, 1. It's 6 ones, followed by a 0. And so whenever the receiver sees this particular pattern of bits, it knows that the very next bit starts the beginning of the frame, and then every 8 bits after that makes up a byte. So for example, if we have this stream of bits, we can just go along here until we see this frame delimiter, and then each set of 8 bits following that makes up a byte. So the frame delimiter is right here. So we can just ignore these bytes at the beginning. The frame delimiter is here, and then each set of 8 bits after that makes up a byte. So there's 8 bits, there's 8 bits, and there's 8 bits. And then we could keep going here if there were more bits. And so so this is the frame delimiter, or the flag, and then this byte right here is 75, this is 65, and then this over here is 248, and so on. We could keep going. So now I did something kind of sneaky here. I don't know if you noticed, but if you look right here, this set of 8 bits is actually another flag. But this flag pattern here isn't here to sort of identify the start of another frame. It just happens to accidentally show up as part of the data we're sending. So how do we send this data without the receiver sort of accidentally mistaking this as a new frame and starting a new frame right here at this 0? So it turns out when you're using HDLC framing like this, there's another rule that we need to follow. Whenever there are 5 consecutive 1 bits anywhere in the data that we're sending, then we should just stuff an extra 0 in after those 5 ones to prevent this problem. So then whenever the receiver sees 5 consecutive 1 bits like this, then it should expect that the next bit is going to be a 0, and it can just ignore it. So if the receiver ever sees like 6 consecutive ones in a row, then it's either part of a flag like this, or there's been something has gone wrong. And so this technique of putting these extra bits in here is something called bit stuffing. So that's HDLC. Now Ethernet is quite a bit different. So let's scroll down here and I'll show you what the beginning of an Ethernet frame looks like. So at the beginning of an Ethernet frame, there's this what's called an interframe gap, which is actually a period of silence where there's nothing being transmitted at all. In fact, the voltage on the wire is zero. And Ethernet requires an interframe gap of at least 96 bit times. So whatever the timing of the bit is, depending on the speed of the Ethernet, this is silent for some period of time. And so that's a way to know that there's no frame being sent, and then as data starts to show up, that a frame is going to arrive. Following that silence, then Ethernet starts to send this preamble, which is 56 bits of alternating ones and zeros. And so you can see the ones and zeros here. And I've taken a capture from the oscilloscope and patched together the entire beginning of an Ethernet frame here just to take a look. And so the preamble is 56 bits of alternating ones and zeros. And this does a couple things. One is it's kind of a distinctive pattern, also following the silence here where there's no data being sent. It gives the receiver an opportunity to synchronize its clock. Because remember, as we start to read bits off the data, when the data shows up, we want to make sure that the receiver's clock is synchronized with the sender's clock. And so this gives the receiver kind of an opportunity to get its clock synchronized among some other things. So there's the preamble of 56 ones and zeros, and so it keeps alternating 1, 0, 1, 0, 1, 0. And then it gets to this point where it continues, where we get to this start of frame delimiter. And so it continues 1, 0, 1, 0, 1, 0. And then the last 2 bits of the start of frame delimiter is 1, 1. And so even if the receiver kind of like synchronizes partway through this, it's going to see this stream of ones and zeros. It may not know where it is among those 56 bits. But eventually it's going to get to this point where instead of alternating 1, 0, 1, 0, you get the 1, 1. And that's the trigger. That's when the receiver knows that the next bit that shows up is the first bit of the data. And then all it needs to do is just start reading the data. And this is exactly what we looked at before. And each sequence of 8 bits forms a byte, and this continues on and on. And so I guess one more thing that I'd like to add is just about frame length. And so the number of bytes that you have in a frame, so once we've synchronized the frame, we have the start of frame, we start having data here, the number of bytes can vary. So like in theory, we could send a frame with just 1 byte. So after this byte, we just go silent. We have another interframe gap. We could do another preamble and have another frame. But that's very inefficient because we have to do this whole preamble nonsense just to send 1 byte of data. So on the other hand, you could imagine, once we've started sending this frame and the receiver knows where the byte boundaries are, we could send thousands and thousands of bytes or even millions of bytes. And that would work too. But the problem is that if any kind of error happens and the receiver misreads something or gets out of sync, then it's going to misread everything that follows it up until the next frame. So there's this trade-off, I guess, between efficiency, where you'd want large frames, and being able to quickly recover from an error, in which case you'd kind of want small frames. So in practice, frame sizes tend to vary between 64 bytes and 1,500 bytes. But in some high-performance networks, you may see frames as large as 9,000 bytes or more, and those are generally referred to as jumbo frames.